In this video, we're going to talk about dipole moments of molecules. A dipole moment is simply um, the degree of separation. So basically, is there a positive and negative, or do they cancel each other out? So individual bonds pretty much always have a difference in electronegativity. The exception to that is carbon hydrogen. Okay, so the exception here is that we're going to say that carbon is basically equal to hydrogen. Okay, and so therefore the molecule, whether something has a difference in electronegativity in dipole moment, is going to be based on its molecular geometry. And so that's what's shown here in this image. So this is carbon dioxide, and even though oxygen's more electronegative than carbon, so blue is more negative, pink is more positive, because of the fact that oxygen's is more negative than carbon, but I have an equal pull in two directions. So I often refer to this as tug of war. So if I have identical twins playing tug of war, you could be there for a very long time because identical twins are usually very similar in build and strength, and therefore there's not going to be advantage of one over the other. And so if you think about the flag in the middle, which would be this positive area, basically wouldn't move. Okay, but basically if you take somebody else, any other two people, okay, let's say a football player versus a cheerleader, okay, typically the football player is going to be stronger, and so there's going to be an uneven pulling. Okay, the flag is almost always going to go towards the football player. No offense to cheerleaders, just football players are stronger. And so that's when I'm going to have a net dipole moment. Okay, and so this example here is water. So oxygen's more electronegative than hydrogen, and so for hydrogen's a special case because the only electrons around hydrogen are in this bond. Okay, there's no lone pairs here at all, so this is the extreme example of that. And so, but because of the molecule is a bent molecule, okay, because when I draw the Lewis dot structure of water, it's drawn like this. Okay, so this is bent with two outside atoms and two lone pair. Okay, and because of the fact that it's bent, there's going to be a net dipole moment. So this part is always negative and this part is always positive. Now, for the terms here is no net dipole moment, I'm going to call nonpolar. And for a net dipole moment, I'm going to call polar. Okay, so I'm going to ask you, is a molecule polar or nonpolar? And so if it has no net dipole moment, then it's going to be nonpolar. If it has a net dipole moment, it's going to be considered polar. And since it's basically going to be considered based on the molecule shape, we can go through here. Okay, now these are generic. Okay, so AX2 means I have two outside atoms. So this would be the linear family. This is, oops, I'm sorry, this is not. This is the linear family. This is the trigonal pyramid family. Here they are, they're already here. Tetrahedral, trigonal pi pyramid, and octahedral. Okay, and so pretty much anytime that I have only two atoms, then it can be non-zero. So we're going to say this is polar. 0 is going to be nonpolar. And the assumption here is all outside atoms the same. Okay. So anything can be read as can be non-zero is considered to be polar. Everything that can be read as 0 is going to be considered to be nonpolar. Okay. And so here's listed by the shapes. Now, to me, this is a little bit harder. To me, if you go back to this table, it's a little bit easier. Okay, so this is going to be nonpolar. This is going to be nonpolar. This is going to be polar. This is going to be nonpolar. This is going to be polar and polar. And so you can see a trend already, the fact that if it has zero lone pairs, all outside atoms are same element, it's going to be nonpolar. I cannot say the opposite. I cannot say that if it's any lone pairs, that's going to be polar. But I can say that most molecules with lone pairs will be polar. Two exceptions. And I'll show you what those exceptions are on the next slide. Okay, so if you have your table of shapes, you might also want to put down whether they're polar or nonpolar. Okay, and so this one's going to be nonpolar. This one's going to be polar. This one's going to be polar. This is one of my two exceptions. This one's nonpolar. So this is an exception. Lone pair, but not polar. And it's linear, okay? So that's why on the previous slide, both linears were polar. Or, I'm sorry, nonpolar. Okay? And for the last table, this is going to be nonpolar. This is going to be polar. And here's the other exception. This is nonpolar. This is an exception. Lone pairs, but nonpolar. Okay? And that's because these two are, oops. And for the exceptions, that's because these two pull oppositely in each direction, and these two pull oppositely in each direction. And since it's a plane, that's an even pull. In the linear, it's the same thing. This is a linear molecule, meaning it's all in one dimension or all in one plane. Okay, and so these two pull opposite directions of each other evenly. Okay, so even though it has lone pairs, the shape makes it nonpolar. Okay, and I also want to say the fact that I need more room on the next slide. Okay, so let me show you the other thing that I was saying about the fact that, two examples. If I have CH4, it's carbon with 4 hydrogens around it. And so it's 4 outside atoms, 0 lone pair, and tetrahedral. And it's nonpolar. Okay? If I, however, change just one element, make it CH3F, or chlorine's more common. Okay, so I still have carbon with 3 hydrogens. It doesn't matter which side, but one side has a chlorine on it. And that one, of course, has that. I still have 4 outside atoms. I still have 0 lone pair. It's still tetrahedral, but it is polar. And it's polar because of the Cl. Okay? If I go to, I'm going to room on this slide. If I go to CCl4, that one's also nonpolar because it goes back to being just like that. The only difference is I have 4 Cls. So that's what I was saying here when I said that I'm assuming that all the outside atoms are the same. Okay? So this is only true when all the outside atoms are the same element. Okay? In the next video, we will be working some